Okay, so we are going to move on from our lesson from yesterday. We're going to build a little bit more. Now we're going to start doing the actual calculations that are required to do in stoichiometry. So we're going to take a look at a couple different formulas. The only notes I'm going to write today are in this little box, and then I'm just going to go right in and do a bunch of example questions with you. So the first formula that is very popular in the chemistry world is N equals little m over big M. Okay, N represents your amount of a substance. And this is always in moles, okay? When you're writing it down as a unit, kind of like how you write km for kilometer, but the word is really written as moles, but you're always going to write it as MOL. Then we have our little m, which is our mass, so how much of the substance we have in grams. And then our big M is what we call our molar mass. This is always going to be in grams per mole. Our molar mass, you will always be able to find on the periodic table. It's the total atomic mass of your compound. For example, if you were to look on your periodic table right now and take a look at hydrogen, hydrogen has an atomic mass of 1.01. Therefore, its molar mass would also be 1.01. But if I had hydrogen mixed with oxygen, giving me hydroxide, my molar mass would be the atomic mass of the hydrogen plus the atomic mass of the oxygen, giving me an overall molar mass of 17.01 grams per mole. So it's on your periodic table, and it is the same as your atomic mass. You find this at the bottom of the element square. This formula, you can also interchange it to solve for mass. I will give you these formulas for a test, but I will not tell you what they mean or their units. You are responsible for knowing that. The second formula that we need to take a look at, so a lot of the times, and what you're going to see is we need to convert between moles and particles, right? Where moles is our N value. We need to convert between moles and particles. So particles, there are three different ways that we are going to talk about particles. First of all, you will hear them be called formula units. Particles are called formula units for ionic substances. Ionic substances, remember, is when you have a metal and a non-metal. The second thing you could have is you could have molecules. You're going to call the particles molecules whenever you have molecular compounds. Molecular compounds are two non-metals. Then lastly, we have atoms. We refer to particles as atoms when we are only talking about a lone element. So it's not a compound, we're only looking at an element for that. So there are three different ways that we're going to talk about particles. This is not going to be given to you on a test. You do need to know this. There's a formula that goes along for solving the number of particles. So our number of particles equals our little n times a new value, big N with a capital A subscript. This stands for Avogadro's number, which we know from yesterday is equal to 6.02 times 10 to the 23 particles per mole. Remember, that particles is either going to be formula units, molecules, or atoms, depending on what compound or element you have. You can also rearrange this formula to solve for moles. Like such. I will give you this and this and this on the test, but you will not be told the formula units, molecules, anything like that. You do need to know that. So with that being said, I'm going to dive right in to the first example. We have a lot of examples to go through this lesson. So if you find that you're really understanding them, you could probably skip some parts of this lesson, but I do start with easy questions and then they do get increasingly more difficult as I go through the examples. So first we're going to look at calculations with the mole and Avogadro's number, and N. So how many molecules of carbon dioxide are there in 4.56 moles of CO2? So how many molecules, so I'm really looking for the number of particles, are there in 4.56 moles of CO2? So I'm going to write my formula because I need to solve for the number of particles, right? Since I know that if I'm asking how many formula units, how many atoms, how many molecules, I'm really asking for the number of particles. So our number of particles equals N times Avogadro's number, where we are given our mole value is 4.56 mole, and Avogadro's number is always 6.02 times 10 to the 23 particles per mole. It is very important that you are writing your units. You have to show the cancellation of your units in chemistry at every step that you're doing it. You need to include units and you need to write your answers this way for full marks. So now I'm going to substitute in my values. So I have 4.56 mole times 6.02 times 10 to the 23 particles per mole. Now you can see my mole cancels out, and I'm left with 2.74 times 10 to the 24 particles. But we are not done. We will never express our final answer as particles. So since CO2, carbon and oxygen, are two nonmetals, we know that we actually have 2.74 times 10 to the 24 molecules of CO2. By convention, you always write the symbol beside your answer of how much or of whatever you're looking for in chemistry. This would be full marks for a full answer. So you want to make sure that you are writing the formula, showing all your work, and then expressing it as a final answer with your right units and writing down what you know. Keep your work very organized. That way you don't mess up. So I'm going to move into the second question. So now I'm being asked, how many moles of water are 5.87 times 10 to the 22 molecules? Right, so how many moles, so I'm looking for the number of moles, are in, so I was given my number of particles. Remember that molecules means particles. So my number of particles is 5.87 times 10 to the 22 particles. And then I always know that Avogadro's number is 6.02 times 10 to the 23 particles per mole. So for this one, I'm solving for N. So I need to use the rearranged version of our formula this time compared to the first one. It's slightly more difficult than the example from above it. So N equals my number of particles over Avogadro's number. I'm going to substitute in my values. So I have 5.87 times 10 to the power of 22 particles over 6.02 times 10 to the 23 particles per mole. I have all of this division going on here with my units. Instead of dividing by particles per mole, you can multiply it by the reciprocal. So you can think about, for your units, instead of having particles per mole, you're going to change it to being times mole per particles. This way, our units nicely cancel out, and I can just divide the numbers to get my answer. So I end up with 0.0975 moles of water. Now, I had 3 sig figs to start with. I want 3 sig figs to end with. So a lot of times you might see this expressed in scientific notation, 9.75 times 10 to the negative 2 mole of water. All you have to do to get from here to there is move the decimal over. 1, 2. Every time I move the decimal over, I increase the exponent. And if I'm moving to the right, they are negative. If I'm moving the decimal to the left, they are positive. So that's how I end up with 9.75 times 10 to the negative 2. Our third example, so how many atoms, right? We're talking about particles. Now it's asking me how many atoms of carbon are there in 1.23 moles of, this is glucose, just for your reference, in this big molecule. So it's asking me how many atoms of carbon there are in that many moles of glucose. So we're still going to write out what we know. So I know that there are 1.23 moles. All right, and I also know Avogadro's number, which is 6.02 times 10 to the 23 particles per mole. I'm going to use my number of particles formula to solve for the number of particles, except what I'm solving for right now is the number of particles, or the number of glucose molecules. So there will be a step 2 after that. This is step 1. Step 1 is we need to find out how many molecules, right, or the number of particles of glucose. So I'm going to sub in my numbers. So I have 1.23 mole times 6.02 times 10 to the 23 particles per mole. My moles cancel out, and I am left with 7.40 times 10 to the 23 particles. I'm really going to write this as 7.40 times 10 to the 23 molecules, but this is molecules of glucose. It was asking me how many atoms of carbon there are. So if I have 7.40 times 10 to the 23 molecules of glucose, how many carbon atoms do I have? Well, there are 6 carbon atoms, right, in glucose. It has a subscript 6. So I know how many molecules of glucose I have. Now I can figure out how many individual atoms I have of carbon if I just multiply that number by 6. So all I'm going to do is I'm going to take 7.40 times 10 to the 23 molecules times, so I have this many molecules per 1 glucose times I have 6 carbon atoms, times, actually, I'm not going to write it this way. I'm just going to show you how I convert it afterwards. 6.40, so I'm just going to do this all times 6, right? Because I have 6 carbon atoms. What I end up getting as my answer is 4.44 times 10 to the 23. Now, I don't have molecules, I have carbon atoms. So the cancellation that I was going to show you is, so there are 6 atoms of carbon per 1 molecule. And you could cancel those out. And then you know that you're left with C atoms as your units. All right, now we kind of ignored our little formula that we had on the left. So we're going to do some practice with those calculations. So what is the mass of 2.34 moles of carbon? So what is the mass? I was given the moles. And I can find my molar mass by taking a look on the periodic table. So the atomic mass of carbon, since I'm only talking about one element, is 12.01 grams per mole. Now I can solve for mass. Remember that when you rearrange this equation, mass equals little n times big M. So I have 2.34 moles times 12.01 grams per mole. I cancel out my moles and I am left with 28.1 grams of carbon. And that's all there is to it. Now let's take a look at our next example. Again, they're going to get increasingly a little bit more difficult. This one is pretty simple. If you want to give this one a try on your own, pause the video and go ahead. So it's asking us how many moles of magnesium is 4.61 grams of magnesium. So we don't know our number of moles. We know our mass is 4.61 grams. And we need to find our molar mass of magnesium. So if you look on the periodic table, the atomic mass of magnesium is 24.31 grams per mole, which is our molar mass. So I need to solve N equals M over M. So I have 4.61 grams over 24.31 grams per mole. Again, I have a division and another division. So instead of writing it like this for my units only, I'm going to do times mole over grams, and now my grams would cancel out for my answer. And I am left with moles. If I put this into my calculator, I get 0.189 mole of magnesium. Notice how every time I am expressing my answer with the right number of sig figs. That is very important as well. So we're going to move on to the next example, going a little bit more difficult. So how many moles, so we're solving for moles, are in 5.69 grams of, now we have NaOH. So when we go to find our molar mass, we're going to have to find the molar mass of sodium and of oxygen and of hydrogen. So sodium is 22.99 grams per mole. Oxygen is 16 grams per mole. Hydrogen is 1.01 grams per mole. All I need to do is add these together. I have one of each in my compound, and that's going to give me an overall molar mass of 40 grams per mole. Now I'm going to go ahead and solve. N equals little m over big M. 5.69 grams over 40 grams per mole. I'm not going to write it this way for the units. I'm going to do times mole over grams. That way my grams cancel out nicely and I'm left with moles. Now I'm left with 0.142 mole of sodium hydroxide. And this is how you would write your answer. We only have a few more problems left. We're going another little step further here. So it's asking us how many grams are 3.5 moles of copper 2 chloride. So how many grams? So we're solving for our mass. We know our moles, 3.5 moles of copper 2 chloride. So remember that this 2 means that copper has a +2 charge, right? And then if we look on the periodic table, we know chlorine has a minus charge. So when I cross my charges, I end up with CuCl2. It's very important that you get this right, because you're going to see when we do our molar mass, we have 2 different elements. So I need the molar mass of copper. If I take a look on the periodic table, it's 63.55 grams per mole. For chlorine, I have 2 of them. So I'm going to have 2 times the atomic mass of chlorine, which is 35.45 grams per mole. So if I do 2 times 35.45, I have 70.9 grams per mole of chlorine. Now I need to add the molecular mass of copper and of chlorine together to give me a total molecular mass for the compound, molar mass for the compound, 134.45 grams per mole. Now I can solve for my mass. So mass equals N times M, 3.5 moles times 134.45 grams per mole. My moles cancel out, and I am left with 470.6 grams of copper 2 chloride. But this is not the right number of sig figs. This is not the right number of sig figs. So our lowest number of sig figs that we were multiplying with was 2. So we would round this to 400. So we have 471 grams of CuCl2. That brings us to 3 sig figs. So we would express this as 470 grams of CuCl2 with the right number of sig figs. Example number 5, how many atoms, remember that this means particles, of lithium are in 1 gram of lithium. So we're given our mass. We are not given moles. we are also not given our particles. But what I can find is our molar mass. So the molar mass of lithium, if I look on the periodic table, is 6.94 grams per mole. And if I use these two numbers, I can use them to solve for the number of moles. And then once I have the number of moles, I can use that and Avogadro's number to solve for the number of particles. So step one, we need to solve for the number of moles. I'm going to use N equals little m over big M, 1.00 grams over 6.94 grams per mole. I'm not going to write it like that. I'm going to go times moles over grams. And I have 0.144 mole of lithium. Now that I know how many moles I have, which is my N value, I can solve for my number of particles, right? Because I also know that Avogadro's number is 6.02 times 10 to the 23 particles per mole. So my number of particles equals my N times Avogadro's number. So 0.144 moles times 6.02 times 10 to the 23 particles per mole. My moles cancel out, and I am left with 8.67 times 10 to the 22 particles of lithium. Remember, I do not express my final answer as particles since it's a lone element. I'm going to express it as 8.67 times 10 to the 22 atoms of lithium. Great. We are on to our last example, which in theory is maybe the hardest one. So it's asking, what is the mass of 3.45 times 10 to the 22 atoms of uranium? So I'm asking, I need to find out what the mass is. Remember, the atoms means particles. So I know that my number of particles equals 3.45 times 10 to the 22 particles. Well, if I want to know my mass, that means that I'm going to need to find the number of moles of uranium. How do I find the number of moles when I was given the number of particles is N equals number of particles over Avogadro's number. Because I know that Avogadro's number is 6.02 times 10 to the 23 particles per mole. So I'm going to substitute in my values. So I'll have 3. This is step 1, by the way. So 3.45 times 10 to the 22 particles over 6.02 times 10 to the 23 particles per mole. I'm not going to write it this way for my units. I'm going to go times mole over particles. I cancel out my particles and I am left with 0.0573 moles of uranium. Right? Or you can write it as 5.73 times 10 to the negative 2 moles of uranium. Right? So if I were to take this decimal, move it 2 places to the right, that means that I have times 10 to the power of negative 2, which is how I get that answer. Now my step 2, I need to solve for mass. So I know that my number of moles is now 5.73 times 10 to the negative 2 moles. I need to solve for my mass. And if I look on the periodic table, the molar mass of uranium is 238.03 grams per mole. So when I'm solving for mass equals N times big M equals 5.73 times 10 to the negative 2 mole times 238.03 grams per mole. My moles cancel out, and I am left with 13.6 grams of uranium. And that is it. We're going to finish off with this for today. There is this practice page, moles calculation practice. I very, very highly encourage you to solve for this. I put a lot of different formulas on here just to show you how they're all rearranged. Remember that this is really an A for Avogadro's number. But good luck, and I will see you all next week.